All right, good morning. Okay, I think that's correct. So, welcome everybody. On a roll here. I got a few things I want to still teach that I think is valuable to you. So let's kind of look at this schedule real quick. It's scattered. I apologize. And this is what it is. For Thursday's the holiday. I'm gonna post a makeup test that we talked about last time. I'll just post that online. Like a 1 hour, you gotta get it done in the time slot. I'll mix up the questions, blah blah blah. You know how they do that stuff. Um, and 60% maximum of the midpoint. So if you got a 90 and you only, the best you can do is like 96%, 6 points. If you got a 40, this means a whole lot. So this is intended intentionally to help my struggling students who did poorly on the first test. That's what it's for. It's worked well in the past 15 years that I've done it this way, so we'll continue the process and tradition. If you've done well, it's probably not going to be a big deal to you. If you got 100, it can count 0 points. not worth it at all. So for those who've done well, but you also, if you did poorly, you're not going to get an A out of it. You're not going to get a first test. You're not going to get stuff at a 90 because that's not fair to the ones who on the first test. So this helps balance out the load a little bit so that we can kind of move on. Same stuff that was on the first test, study for, do it again. Or not again, but study for that same stuff. I have to get a second test in. It looks like I've got to stuff them in here. It will most likely be a week of Thursday. 99% sure. Okay. I do like to do a little bit of review. I think that's always important. It's not going to be an entire class review, but it will be a little bit of review. And then we'll do test number 2 in here traditionally. Primarily everything that we've done since the first one, primarily sewers, slope, grading plans, cut and fill, volumes. Those are some pretty good topics. This is a very important practical application test. Those folks do pretty well on it. Okay? Those folks do pretty well on it. But it's the practical application stuff, the volumes, the areas, the slope, computing slope, computing sewer, inverts. Still need to read the tape measure, and you still should be able to input. So those, whatever, 6, 8, 12 topics are important. I will do a little bit of review on Tuesday when we come back next week, a week from today, so that you've got something to study for. But we'll do that on next Thursday. Get that thing done. The following week, I know people are trying to scatter and stay and go. And it's like this every year as well. I'm fine with it. I will be here on that Tuesday morning. I don't know what I'll talk about. I'll probably put it on video on YouTube or whatever. It's probably anything that I don't get to today, probably. But it's pretty light. But Tuesday and Wednesday and lab, it's open. It's just open. Okay, I'm not going to go over anything new. It's just if you want to come and try to get your projects done and accomplished before you go to the Thanksgiving break, that seems pretty good to me. I do have today in lab, we've got to finish the profile. So now Tuesday's group is behind. Wednesday and Thursday are now the ahead groups. So they've already done the profile. So Tuesday, you have to be there this afternoon and get your profile started so that you understand how to do that. Next week is a full week. So I have one little topic on the detail, how to do the detail. It's a short cut and paste almost exercise. It's not a real big deal. Not a heavy topic. So I also will be doing. Usually I put about an hour into that, maybe, for the detail, and then I'll have the robots and GPS stuff with me, and I'll just keep them on Tuesday, Wednesday, and Thursday. So if anybody in lab sessions, if you're Wednesday and you want to come on Tuesday and look at the demo, that's fine. I'm happy to do that. But we'll go over weather permitting to Burnett and do a demo for some robots and GPS. It's fun to see it, touch it, move it, watch it. I don't know how much you'll learn from it necessarily, but we can kind of take a walk past the construction site, see how that's going, to compare what we're doing with what they're doing, with how we would do it with our equipment. So I just want to get that in front of you because I think it's pretty interesting. Did I bring the laser scanner in, by the way? Did I have that laser scanner? I did not bring that in. You did not know if I said that. So I will probably do that at some point. I might even do that right here. You can get that stuff online. You can see that there are plenty of other people that do this stuff. That's probably a good day for me to do that right there. Like that. Okay, so Tuesday we're going to do. Next Thursday will be the second test in class. Lab sessions will be detail and then some demo. The Tuesday and Wednesday prior to Thanksgiving, I'll do probably the laser stand right here. But the lab sessions are open. Anybody from any of them can come to any of them. If you want to try to get something done, print it. Gets a little bit busy sometimes, but it's Thanksgiving, so some people aren't there. The following week, that Thursday, projects review. Basically, it's the last day of class, of course. And when I say do, I mean kind of do. You want to turn them in on Tuesday or Wednesday, that's fine. You don't have to wait until Thursday. But I will give you Thursday's group lab sessions or whatever. I'll give you that extra time. I personally try to get them done here. Look at them over this. Maybe print here and hand in there, or maybe print here and hand in there. Okay, so I try not to leave all that stuff sitting on my head, trying to get done. I will remind you, it's very important that there is a report that is part of that project. So you've got sheets of paper. We'll talk about that next week. But there is a report. It's a reflection of what you've done for the last 15 weeks here. What did you learn? What did you not? What did you like? What did you not like? Who did you like? Who did you not like? What went well? What went poorly? Where do you see this taking you? All that kind of stuff. A little bit of a reflection, about a 1.5, maybe 2 page of reflection, just so that you kind of got it in your head what happened. Again, these are for you. You're going to keep them so that in a year or 5 years or something, you dig through your crap and you look back on your college experience and say, oh yeah, I remember we worked on that project. You kind of you'll read that report and you'll say, oh yeah, I remember all of that happened. It's just a really good archive thing to put in your better than the textbook that you'll never use to cover the back. So there is a report that's due. If you want to start writing that, that's okay. Most people start to not use like that. All right, so that's when it's due. We will do a review for the final. All right, final is as posted on UC's website. It is by UC's rules. I don't change that. So that's when it is. I think it's from 8 to 10, I believe, right here. I'm pretty sure it's on December 7th. Double check that for me. Something that's there. All right, so we'll do a review here and lectures, and then whatever else I don't get done, the lecture up here I'll get done. So that's what the game plan is here. Are there any questions or comments or problems? Am I missing something? Yell at me if I am, because I'm pretty scattered these days. Okay. I have two topics that I want to talk about today. 3 if I get to it. 2 for sure, 3 if I get to it. There is one thing that I've missed that I want to share with you. If you remember a couple of weeks ago, I did the Prismoidal formula. I think that's something that is very handy, that particularly for civils and CM to have as a tool. We don't teach that in math class. We try to always teach real length, width, and height stuff. Our work's a little more complicated. So the Prismoidal formula is a really good tool to keep. I probably expect it on the final. I probably expect it maybe even on the second test, right? But we've been talking about it, and I'm going to say it's important. So I think it's a good tool to have to compute volumes with. There's one thing that I missed, and it's similar in nature, and it's called the area by coordinate. I've been talking a lot about coordinates for these several weeks, and everything in the industry is really coordinate driven and coordinate based. Rest. And it's pretty handy. Now, I'm not going to develop this for you. I'm just going to simply use it and show you how it's done. It's pretty straightforward. If I try to explain it, it's complicated way too much. If you are so inclined, you can look it up. It's called the double meridian distance. But an area by coordinates is really the best. So let's suppose I've got a figure of, I don't know, it could be anything. 3 to 19 million sides. I'm just going to make it a simple four-sided figure. It could be any shape. Let me assign some coordinates to it. Let's make this fairly, fairly small. Let's make this make this 145 north and 75 east. Let's make number 2. It's not nearly so far north, so let's make this about 85 north, and let's make this thing about let's call it 30. These are northeast and east. Really don't matter. Let's make this one about 22 north and probably 107 east. And let's make this one maybe a little farther north and go to these two. Let's make this 103 north and about 190 east. Now, we've been doing a lot with coordinates, how you get those, all of that kind of stuff still applies. But I have a four-sided figure with coordinates that I want to try to determine the area of. Now, again, what your coordinate system is and all that kind of stuff is to be determined. But we're using northern and eastern. So it goes like this. What you want to do in order to use this is to list coordinate points. I'm going to give myself a little bit of space. You might want to as well. So I've listed the coordinate points, 1, 2, 3, and 4. Now, here's the thing that you got to do. Again, I'm kind of just telling you how to do it, not so much why. But we have to go back to number 1. You have to close the figure. You have to repeat the little asterisks by there because you got to repeat that first point. No matter how many you have to come back to the beginning. You have to repeat the last coordinate. Next step is to now, what we would call, what we would call cross multiply down and to the right. So we're going to cross multiply down and to the right. I'll get you into it. You're going to get your calculator and follow along. That's probably a wise idea. A little muscle memory to it. So, got my figure, got my coordinates, I list my coordinates, 1, 2, 3, 4, or whatever. You have to repeat the last one. That's a big deal. Cross multiply now down and to the right. And then we're going to simply sum up those numbers. 22, 300. Do the same thing down and to the left. watch my numbers. I'll get a lot of buttons as well. Check me. Multiply down to the right, multiply down to the left. Sum up the numbers. Did I do that correctly so far? That summed up these two numbers. Now we want to take the difference between those two. We want to take 45,606, that 25,350. And we're going to divide that in half. That's it. We're done. Again, I didn't develop it. I'm not trying to develop it. What you don't really want to do is try to break this thing down into triangles or simple pieces. You can compare if you want to try this on something like that. See if the method works. I encourage you to do so. I will tell you that this is how AutoCAD does the area. When you do the area command, it's click, 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 click. It does this. What it's doing, it comes up with an area of a figure. So again, just take the figure with the coordinates, repeat the last one. That's where most students forget, fail, and miss. Miss the right that cross multiply down to the right, and add them up. Cross multiply down to the left and add them up. Take the difference between those two values. Really, you see an absolute value of nothing. And then divide it in half. It's a double meridian distance, so we got to subtract. Divided by 200. So we take half of it. And the number that we get is the area in square units of whatever you work. You work in meters, you do square meters, you work in feet, you do square feet, etc. So if this were square feet, one last thing we may occasionally do, only because I want to talk about, you got to remember how many square feet are in an acre. No, of course not. 80 square chains. Talk about change in a minute. All right, so it's 43,560. I would give you that, of course. So if we wanted to know how many acres this is, it's about a quarter of an acre lot. Pretty small. 335. Square feet or acres. Area by coordinates. Kind of like just do it this way because I told you. Not hard, but I think it's kind of useful. It's a nice tool. It's kind of like the Prismoidal formula. I didn't develop it either, but it's a nice formula for you to use and keep and to have and to be tested on. Makes a great test question because, well, now this does have a right or a wrong answer. And you can cross multiply and add up, divide by 2 pretty well. So, hey, I was a teacher, I put it on a test. All right. So we've got 2 scattered topics. We've got to pick up a few things we've missed. All right, last time, last class, when we ended, we were talking about the geoid, and we were talking about the surface. We were talking about the ellipsoid, and we talked about the geoid. Remember that picture? I think I even had it on. Oh, wait, there it is. Perfect. Okay. So we talked about when we look at numbers that NGS gives us, we said that the location is really based on latitude and longitude. When we talk about geodetic survey, GPS, really the coordinates that it computes are latitude and longitude. That's where it gets its computations from. And they are in degrees, minutes, and seconds, decimal seconds. So when we look at a coordinate, it's an NGS, it's a latitude, longitude, and it's in degrees, minutes, and seconds. It's an angle. How many degrees? Longitude and the Greenwich Meridian. By the way, that's an interesting story. It came big fight between Paris and England and London. Who was going to get England? Who was going to get 0 time? Who's going to be the timekeeper? We have time change this week. We had time change this weekend. Quite a big argument. Somehow, I can't remember all the details, but somehow Greenwich England won. They ran a line down the middle of the library in Greenwich England, and that became 0 longitude, and that's where we measure everything from. And the timing started from just that place. So then north and south was much easier. Let's call the equator 0. Let's go up 90 to the North Pole. Where most folks live, or 90 down to the South Pole. That's where the other most of the folks live. So latitude was kind of tricky. Notice that we're 39 degrees north latitude. We're less than 1/2 the way between the equator and the North Pole. By the way, this is more of a by the way moment, but by the way, if you go out, particularly in the summer, it's a lot easier to see. And even now you can kind of see it. If you go look for the Big Dipper, most of us can find the Big Dipper up in the sky. You'll find the Big Dipper. And if you take these 2 front stars off of the Dipper, and go out about 6 dips worth, I know that's kind of crazy, but if you go out about 6 times that amount, you'll find a star that's fairly pronounced. It's like kind of by itself. It's pretty much not the brightest one in the sky, but it does have a fair amount of dark space, particularly in Cincinnati around. You don't see too much. It's called Polaris, and it is the North Star. It doesn't move in the course of the nighttime. It does, but it's only about 8 minutes of arc. You can't hardly see it. So as the Earth spins, that star kind of stays right there. And where you go? Now, the Big Dipper will move, and all the other stars around it move. But relative to the position, the spin of the Earth, the appearance is that Polaris is not spinning. It's right there. It's not moving with us. So the axis of the Earth, just by whatever design or chance, at this point in millenniums, kind of goes through that star called Polaris. A little bit of change. So as the Earth spins, it looks like it's kind of right there. Well, from our vantage point from here, again, it's a poor picture, but from our vantage point, it's only about 39 degrees in the sky. Where I get that from? It's about the same as latitude. So we kind of go up 39. Now, 39 degrees is, there's 45, there's 90s over my head. It's still pretty high in the sky, a little higher than you think. So we're kind of bring your head back to see it. But it's a neat thing to know, a kind of neat thing to find out about. Anyway, I say that is because that is true geodetic coordinates. That is where the geodetic stuff comes from. And a lot of times you'll even see this kind of listed as a star when they talk about geodetic north. Now you say, George, north isn't up. Okay. And now north is up. You got to kind of get past that in your mind. The north is always up relative to you. It's really, we're pointing to the center of gravity. We're on the side of the planet, so it just sort of feels like that. But north being kind of like that is what it is. So those are true geodetic coordinates. So geodetic coordinates involve latitude, longitude, and then we usually use ellipsoid height to get us our 3 dimensions. Now we're actually up on the surface, which is orthometric height. So we can use either one of those. So I said all of that because it's really kind of a good introduction to what we're trying to get. So if we do have a spinning Earth, and we do have satellites that are now giving us coordinates, and they are in state plane coordinates, they are in geodetic coordinates. For us to use that is challenging. We can't inverse between 2 degrees, minutes, and seconds, and degrees, minutes, and seconds, 2 latitudes, 2 longitudes, and come up with a physical distance between them. It's doable, but it's really hard. Really, really hard. Geodetic. And it's not practical. So, multiple years ago, 1920s or so, the South Carolina, North Carolina Departments of Transportation were running into issues now that we were getting much longer roads. You only start in one end of the state, you only start the other, and they were trying to measure the distances, and they really weren't taking into account the curvature of the earth, and it's crap, they missed. Things weren't coming together. Like, why are they not coming together? Why are things not? Well, they weren't taking into account the curvature of the earth. So, and again, the mathematics in the 20s was really pretty hard to come up with anyway, so they began a committee, we always do, and they sent it to the Ohio State University. They want the Ohio State University. And that group of people, those geodesists, thought this through and said, what we need is a method of taking and making some plane out of where we're working. What we need to do is to make a surface. I'll use this piece of paper. We need to make a surface so that if I'm working in the Carolinas or in Ohio or whatever, I can somehow make an X and a Y coordinate system, or a north and an east, whatever we want to call it, that is flat and planar, like a piece of graph paper. Maybe I'll just use a piece of graph paper because we're working. All right. The challenge was, and I'll leave that fun that way, just for emphasis here. The challenge was is that what we were trying to get is an AutoCAD grid, a grid paper, a flat, plain grid paper, left and right, up and down. Because Mr. Pythagoras has told us how we can already invert and come up with sine, cosine, and tangent. We did that last step. We invert bearings. And life was pretty good until about the 1980s again, when we went through all of this mess. But anyway, there are 2 methods to represent round with a flat plane, so that when we open it up, it develops into a plane. There are 2 methods to represent round curve, so that when we open it up, we get ourselves a plane. One method is like I just did there, is a cylinder. And some guy named Mercator thought of this hundreds of years ago, because this problem is not new. The mariners trying to sail across the ocean, they just didn't know. So they came up with a mapping scheme so that they could develop at least maybe the middle latitudes. I'll start this way for you. The middle latitudes, so that when you open it up, you got a map. You can roll the map up and see where you were, but you're still representing the curved Earth. So as long as you're on the middle latitude, it's no big deal. But if you got to the North Pole, you got a map. The other method is to take and make a cone out of it. And I'll just kind of show it this way to you. The second method, some guy named Lambert came up with the idea, like instead of doing that, why don't we just take and make a cone? He said, well, how does that work? Well, it still lets you open it up and get a flat plane, but it actually represents, and it's a little bit easier mathematically, because everything points to the north. If I've got a cone, a cylinder, north sort of points here, but if you're over there, it's not pointing to the North Pole, it's pointing past it. But if you take a cone, then everything points to the middle point, which is kind of like the North Pole, or the star, or whatever. So it started to represent. Now we can't take it to infinity, so there is a limitation on this thing. And we can't represent the entire planet, but we can represent a piece of it so that when we open this thing up and develop it. Otherwise, it's impossible to take and make a curved surface out of a flat piece of paper because you get distortion. I know that's dramatic. I've done that 1,000 times, but it's dramatic. You can't represent curved earth, an ellipsoidal shaped earth, round curve, whatever you want to call it, with a flat piece of paper. And yet we need the flat piece of paper. I'll bring this back up right now. We need the flat piece of paper so that when we open this thing up, we at least have a grid system that is an XY plane. And all of that I just said, from Ohio State and South Carolina to trying to map this in Mercator and Lambert, all of that is the introduction to what would be called state plane coordinates. And you've been using them for weeks now. And it's like, well, these weren't even hard. You just give me some numbers and I invert between them. And recap, we had a small site. And if you're under a few miles, that's a small part of the earth. Okay? So this works for miles and miles. Now, when you start dealing with GPS and we're hundreds of miles apart, much more complicated. But for something the size of the state of Ohio, state of Kentucky, state of Indiana, there are different methods of either taking the projection as a cylinder or a cone, but every state has a plane coordinate system so that their entire state can be represented in some form or fashion with an X and a Y, or a northern and an easting coordinate system. Now, Ohio actually has two. The idea here is that we limit this distortion to a precision ratio. Now you know what that means. We can limit that distortion to a precision ratio of about 1 in 10,000. So we only lose about a foot in about 2 miles, 1 in 10,000, which is pretty good. Okay. You remember what you were getting for your precision ratio running the Traverse? And a couple of you got 1 in 3,000 or 4,000. You thought you were hot stuff. That's pretty good. Right? And that was just the small stuff. So this mapping scheme is pretty tight. 1 in 10,000 is pretty useful. It's generally useful for everybody except a couple of anal surveyors that are out there. But we'll talk about that in a minute. But in order to do that, the state of Ohio had to create 2 zones. So they created a north and a south zone that overlaps just a little bit. So if you're working out of Columbus, it's pretty freaking ugly because you all know you're in the north zone and the south zone. You have different coordinate speeds. Things are just skewed a little bit different from that curvature of the earth. The placement of that cone and the size of that cone and the radius of that cone become important to hit that 1 in 10,000. We are not going to talk about that. If you want to get into surveying, go to Cincinnati State and take some of their classes because they've got a great program of surveying. But that's not what we're trying to teach here. We're just teaching basic introduction stuff. But we're trying to take this cone, trying to pass it over. Now, the size, the shape, the configuration. Now, it makes sense that north and south hits that. So if we go to the middle of the state somewhere, and we take our cone and we line it up with that north, geodetic north, Polaris, quote unquote. We line it up with geodetic north. That's pretty good, but we can't get all the way up to geodetic north because the North Star is like at infinity, right? It's way beyond that. But the cone touches somewhere. The cone touches somewhere a few thousand miles out in space. And I said all of that to say this: when I open this cone up, everything is pointing to the center of the cone, not the star. This is called grid north. So if I'm in Cincinnati, I point to the middle of the cone. here is grid north, pointing to the middle of the cone. Astronomic north points to infinity. If I'm over in Athens area, grid north points to the middle of the cone. Astronomic north points at infinity. So the one deal that we got to deal with is the fact that if we take a shot on Polaris or geodetic north, we need to know what this angle is because it's changing everywhere. I happen to be in the middle of the state somewhere on this issue. They're the same. That's good. You're not in any correction. But as I move towards east and west part of the state, I deal with that. Right? It's called the convergence angle. And when you look at state plane coordinates, it will give you a convergence angle at that specific location where benchmark UC was, minus and this is in degrees, so it's 1.2816. Okay, so it's in decimal degrees. So you have to convert that to degrees minutes per second. It's about a degree of diversion difference. And we're about as far west as you can go in our state plane coordinates. So it's only 1 degree. It's a pretty small amount. But it's still 1 degree. It's still an amount. So they give that for you everywhere. So that's kind of what that means. That's kind of handy. Knowable. So if we were to take a shot on Polaris, we'd have to go a degree, 0.26, about a degree and a half, and we would be then pointing to the center of the cone. We'd be on the grid. One of the neat things about this is that we can minimize that distortion. There's really 2 things that we worry about in our world. One is angle or bearing, and one is distance. The third would be area, but we can't control that. We only get to pick 2. So with this cone system, state plane coordinates, to hit 1 in 10,000, you get bearings and distances. I can deal with that because I can work myself in grid bearings, and the angles are not changed. So whatever I measure on the surface, if I measure a 62 degree, 15 minute and 40 second angle on the grid, it's 62, 1530. Okay, so the angles hold; they are not distorted. The distance is pretty daggone close. It's going to be 1 in 10,000. But I'm going to show you something here. The second part of the conversation. Distances are controlled to about 1 in 10,000. We can even beat that here in a little bit. So if I measure something on the surface, or at least on the near the surface, near the ellipse anyway, when I transpose that to the grid, I'm going to be within 1 in 10,000. 99% of the time, that's close enough for anything you all will ever do in your careers. There might be one surveyor who's running geodetic control over Hamilton County, but that might be a freaking deal. But the rest of the time, nobody even cares. Most of the time, nobody cares. All right. So that's kind of an introduction to that. Let's look at an application of that and get back to where we were. So the angles hold. We don't have to mess with them. The distances we started to talk about. So last time I showed the surface, I showed the ellipse, and I showed the geoid. We said that the geoid in the continental United States is negative. It's the geoid, it is below the ellipsoid, except in Death Valley. It's a negative one. What we call orthometric height or elevation is measured from the geoid. The geoid is sea level. It's what we would call sea level. It is the representation of sea level. While I hate that term, it does seem to make some sense. At least it's the new version of sea level. It's where we measure elevation from. Right? It's called sea level. It's really the gravity model of the Earth. Right? So if I have the ellipsoid height and the geoid height, ellipsoid height is from here to here. Should we show that on there? So if I have the ellipsoid height for the receiver, use this GPS if you use it, and at any point I know from NGS, they tell me the geoid height. They measure that based on gravity within about year months for everything. So they tell me the geoid height. If I take the, if I add the absolute values on it, I come up with what's called the orthometric height. So we would say then that ortho height, elevation, is equal to the ellipsoid height minus the geoid. And I'm going to put minus in there because it's going to be a negative value all the time. Measuring that value. It's going to be a negative value. So you're literally adding ellipsoid and geoid together. Make a note to yourself, explain that to yourself right now in your paper. You're going to study that. Obviously, I'm going to ask that somewhere as a test question. And you got to remember, don't argue, keep the things like that. Make a note to yourself. Orthometric height, geoid to the surface. The ellipsoid minus a negative geoid. Give you the orthometric height. Okay. All right. Now, there is a place where the plane cuts through all of this point. So that was all geodetic. Now we're going back to state plane. So there is a place where that plane, where that cone touches that surface. There's a place where that cone, and I got to kind of show it this way for emphasis, but there's a place where that plane touches and represents that curved earth. And that's called our grid. Called our grid. Grid is the map. Grid is the X1. It is variable everywhere. So over here, you kind of get a little bit of negativeness. In the middle, you get a little bit of positiveness. Over here, you get a little bit of negativeness. The difference between those two is called the K, or the scale factor. The difference between those two is called the K, or the scale factor. It varies everywhere you go because it only touches, the flat plane only touches the curved surface in two spots. 1 and 2. And that's like in Chillicothe and I don't know. Okay, it's like across the entire state. There's only a couple of places where that thing touches. Kind of east and west. There's only 2 places where K is 0. Everywhere else is either plus or minus a little bit. It's called the K, it's called the scale factor. Now, I'm not so much worried about that particularly. Again, kind of beyond the scope of what this is. But it too is given. It too is given on an NGS sheet. Some the NGS would give it to you. So since it's location variable, it's going to be given to you. But notice that it is always, don't worry about the UPN. But on their same length coordinates. Notice it's 0.9999, in this case 453. Remember, we're about 1 in 10,000. We're about 1 in 10,000. Tens, hundreds, thousands, 10,000. So this scale factor is pretty freaking close to 1. It's not exact, but it's set up so that anywhere in there, and we're all the way on the west side of the state, even at that, we're still very, very close to a 1 in 10,000 difference. It's almost negligible 99% of the time in your work. It's set up that way. It is designed. But if you're anal and need that extra little bit, it's there. All right, what I want to take a look at, however, I'm going to make a new picture because my sloppy is this last little thing, all the elevation value. All right, so let me reproduce this very, very quickly. Okay. Notice that if I take a distance up on the surface and compare it to the grid, there's a difference. If I take a distance, if I set up a prism and a total station up on the surface and take this distance, the surface distance, I guess. When I project it down to the grid, this is that last 1% of the anal needs of people trying to get everything perfect. If I project that down, this is called the grid distance. And as you can kind of imagine, it's going to be smaller than the surface, because it's kind of going towards the center of the earth by 800 feet. So there is a factor, and again, I'm not going to develop this. And I only say this because a lot of times in GPS you will see this as a setting. You're running two of you that are going to be doing some layout using GPS in your careers. You're going to scroll through these settings, and you're going to see this as a setting. It'll say something like ground to grid. It'll say ground to grid. The challenge in our world is, are we trying to work up on the surface and come up with a map, or are we going to try to get into the state plane coordinate system, which is on the grid? Are we going to work up on the surface? That's where we're making our measurements. When we do our map in AutoCAD or et cetera, are we trying to put it in a coordinate system that's the same, which is what I've been yelling about for 17 weeks? Are we going to take that into account or not? Again, if you don't, it's still only 1 in 10,000 off. But, blah, blah, blah. Very good. R is the mean radius of the Earth. It is the average value of the radius of the Earth. It changes everywhere because it's really an ellipse. So we don't have it's not a circle, it's not a sphere, it's not a ball, but there is an average of it. So there's an average value, the mean radius or the average value of the Earth is 20,906,000 feet. 20,906,000 feet. The average radius of the planet Earth. H, of course, is our orthometric height or our elevation. And N is that geoid height. And again, around here, it's going to be a negative value. It will always be a negative value. So, this will give us a factor that will allow us to multiply our surface distance by to get the grid distance. I'll always write that out. The grid distance is equal to the measured surface distance times the elevation factor. And I'm going to put in here times the scale factor just because that's the correct way to do it. times the elevation factor times the scale factor. Just for completeness so that people know that I know what we're doing here. This is actually called the combined factor. We can put both of those together and come up with a combined factor. Now, let's just do one because this would be a good test question. Let's suppose that we had the elevation of benchmark UC is about 814 or something like that. Let's suppose we're nearby here anyway. We get the elevation is 815.70. Let's suppose that our N factor was let's see what it is here, and I'll convert it for you real quick. Uh, 111.94. All right. So, one, find the elevation factor. Find the elevation factor. Okay, let's do that. So, the elevation factor is equal to 20,906,000 divided by 20,906,000 plus 815.70 plus a negative 11. This bottom, you had a count. You had a spread. 20,906,000 plus 815.70 plus 111.94 negative. Reciprocal times 20 million. Okay, so I just counted that out, both of these up. 20 million divided by 20,906,000 plus 15.7 plus the negative 111. You want to bracket that whole thing, or parentheses or whatever, that's good. And I come up with 9,999,66338. Again, look at this, 10,000, 10,000, we're still 1 in 10,000. It almost doesn't make a difference. Right? It almost doesn't make a difference. It's almost more than you can measure with good tools and skill set. However, let's complete this topic by taking, let's say that the given K factor is this. Again, that's point-based, in the middle of the line that you're measuring, etc. But let's say that the K factor is 9,999,4527. K is 0.99994527. So where we're located here on west side of Cincinnati, K factor of their benchmark UC is 9,999,4527. Let's suppose somebody set up a GPS 1 inside a GPS a benchmark UC and measured 274 feet. Measure 274 feet. The grid distance would be equal to 274 feet times the K times the elevation factor. or times 0.9999 and 0.9999. 4527 and 9999 6638. A lot of nines. On found the elevation factor. Found the elevation factor for this crazy formula. Given the K factor NGS where I'm sitting, multiply those two together times my 274. What the heck do you get? Pretty small number. Pretty small change number. 9999 4527 9999 6638 times 274. Now, I know that's not overwhelming to you. Okay. Pretty small number. Hardly any change. Not even freaking worth it, George. You're right, I guess. But if you look back about 8 weeks ago or 12 weeks ago when we started this, when we inversed between benchmarks from GPS 1 and benchmark UC, I got two sets of independent coordinates I got from GPS. We inversed between those two coordinates. When we did so, we were on the grid. When I gave you the coordinates for benchmark GPS 1, and I gave you the coordinates for benchmark UC, and you inversed between them, you came up 273.98. Personally, I think that's pretty. Because I got a GPS system that I set up, found, turn the thing on, sat there and watched it for 4 hours. Actually, I think I only watched that for 20 minutes, but it's an hour before that. Years later, after they destroyed my benchmark GPS 2, so they put in a new walkway there, I said, oh crap, I'm going to put it in the benchmark. So I got a hole and I put it in the benchmark. And I put concrete, I put it right on the top of it, I put it right on the flame on, standing on there, set the receiver on there. That dropped 4 hours and did the stuff. Sent it off to the AGS, came back, they gave me a coordinate years later. I got a coordinate on that, I got a coordinate on that. We inversed between those. That's the numbers you used week 2 or 3 or whatever we started this project. We inversed between those 2 points and got an angle, a bearing, which doesn't change because it's grid bearing. It's non-distorted. And we got a grid distance of 273.98. I think that's fascinating. Now, the learning, the applied learning, is that if you inverse between 2 points and you're actually working on the surface, you would multiply by the reciprocal of that. So you would go from grid, you would multiply by 1 over what's called the combined factor. And that would be equal to whatever that distance should be on the surface. So if you inverse between 2 points, you're getting the grid distance. You multiply by the inverse, 1 over the combined factor, and you should get the surface distance. I said all of that to say this very last thing for this morning, is that NGS, almost all the time now, takes all of that into account. They give you this stuff. They give you the combined factor. So this combined factor is K times elevation factor. It's already multiplied out for you. It's those big nines put together. It is this stuff that we just did here because they know where that point is. We told them where that point is. So if we multiplied by the reciprocal of that, of our inverse distance, we would have gotten 274.0. And other than some people's inability to look at that big bubble and run industrial, that's exactly what we got. Again, I think that's pretty cool. This is the introduction. This is, if you were going to go into state plan coordinates, if you were going to do something kind of profound and neat, that's what this is. For 90% of you, and 90% of the time, 99% of the time, we are at 1 in 10,000. We never worked that close. Nobody cares. By the way, for construction activities, 1 in 5,000 is a good level of precision. 1 in 5,000, twice that, or half that is good enough. So again, most of these are never going to use it. However, I think it's good to give you something academically. All right. Have a good holiday on Thursday. Watch for that test. I will post it, put it in Canvas. Next week, we got a little bit more learning to do. And we're almost done learning. I'll see my Tuesday's group in lab this afternoon. How'd the arm surgery turn out? Did it hurt?
Yeah.
Yeah?
Yeah. I don't know.
Well, don't do that anymore.
You gonna play it in it?
No, I just tore some tendons.
Yeah. Got a nasty scar.